Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 47 in the series, Graphs of Rational Functions.
So graphical depictions can be useful tools in understanding the properties of new mathematical objects that you may learn. It gives us a nice way of seeing not just the rules of a function, but how to look at all of the outputs quickly given a certain section of the number line as an input. Let's look, for example, at the reciprocal function 1 over x. This function takes in x and gives you its reciprocal, unless, of course, your x happens to be 0. It's one of the simplest rational functions, which are ratios of polynomials, that gives us some cool behavior. To see what it looks like, let's plot some points. Here I've given a selection of points, -4, -2, -1, -1/2, -1/4, 0, which is undefined, and 1/4, 1/2, 1, 2, and 4 here. And if I plot all those points, we get these two curves, a curve down in quadrant 3 and a curve up here in quadrant 1. This function is pretty important, so let's take it down as critical notes. Copy this picture. This captures some of the fundamental properties of 1 over x. As we start to get towards 0, it seems to get really big. As we go towards infinity, it gets really small. It stays positive if x is positive, and it reflects that behavior. It's negative when x is negative. So take into note those key features. There are two separate curves here. It gets broken up, and there is strange behavior around x equals 0. It seems to shoot off towards either positive or negative infinity. We call that a split vertical asymptote. Other things to note, if you have a very large number, you have a small reciprocal, which is positive if the number is positive. If you have a tiny number close to 0, but a positive one, you get a very large number as your output, a large reciprocal. And the same thing is true for the negatives, just of opposite sign. Large negative numbers have a tiny negative reciprocal, and tiny negative numbers really close to 0 have large, in the sense of having great magnitude, negative reciprocals. Another important rational function is the square reciprocals, so 1 over x but squared, which is the same as 1 over x squared. And if we plug in some points here, we see some similar behavior. It gets very small as x gets large. Now, though, it stays positive because a square of a number is positive. And as we go towards 0, both of these seem to shoot off towards positive infinity. Little numbers have huge positive square reciprocals. So we see a vertical asymptote again, but now both branches go off towards positive infinity. And we also notice some asymptotic behavior in the horizontal direction. As you get large, the magnitudes get small in both cases. So in this case, we say they approach this horizontal line, y equals 0, as x gets large, either positively or negatively. We say that when a curve A gets arbitrarily close to a curve B, that it approaches it asymptotically. So let's look a little bit about changing the parameters of this. Let's look at how changing the location of the 0 in the denominator changes the graph. For example, where would this graph have a vertical asymptote? Where would it have a 0 in the denominator? Well, now not at 0, which would give me -1 in the denominator, but at +1, because 1 minus 1 would be 0. If we plug in a few points, we could see then that 0 is going to go to -1. 1 is in fact undefined, and a few other points around this undefined point will give us this graph, which looks very similar to what we had before. But now our vertical asymptote is located at x equals 1. A vertical line, x equals 1, is what it starts to hug as it gets closer and closer to, in x value, to +1. So it seemed to shift the graph. It seemed to move the graph over by 1 towards the +1 when I subtracted 1 in the denominator. Now it starts to look like zeros in the denominator just correspond to vertical asymptotes. That's not exactly the case, though. This is only true when that 0 doesn't cancel. We saw in the last video what happens to x over x. It doesn't have a vertical asymptote. Let's look at a trickier example, a little bit fancier of a polynomial. What about x squared plus 2x plus 1 over x squared minus 1? To see what's going on here, we should factor. So if I factor both the top and bottom, I get x plus 1 squared on top and x plus 1 times x minus 1 on the bottom. Now, one of those x plus 1s could cancel. One of the ones on the top could cancel with this one on the bottom and leave me just a single x plus 1 on the top and an x minus 1 remaining on the bottom. Notice we still have a domain restriction. We are not allowed to plug in 1 or -1 because that would zero out the bottom at some point in time. All right, so let's plot some more points. Let's see what we get. Plugging in the following points, I get certain values as a output of my function. And here I've plotted them over here. Now, at the canceled point, x is +1 because we had a x minus 1 canceled on the bottom. There's a vertical asymptote still. But at this point over here, x is -1. Now there's going to be a bit of an issue. It would have given us a 0 if this canceled version of the function was the full story, but it's not. We got here by canceling. And that canceling means that this value here, we aren't allowed to plug in -1. And so we have a hole here. A canceled value is still undefined at this point, but now we just have this hole. So let's take some more critical notes. Copy this down. Let's have a rational function r of x is equal to a polynomial p of x over q of x. Now, wherever q of x is equal to 0, that's the denominator, x is restricted from the domain. The domain would be all my x's except for the ones that made the denominator 0. And if such an x is of the form of an uncancelled factor, so in other words, if you have an x that makes it 0 on the bottom and it doesn't also make the top 0, then you're going to have a vertical asymptote of some kind. Now, on the other hand, if you cancel a factor that has an x on the top and bottom, like the x over x or the example we just saw, there'll actually just be a hole in the graph. So I have a kind of playful praxis for you today. You don't have to copy this down. What I'd like you to do is I'd like you to go to Desmos, and I'd like you to graph this function. I'll show you how to do that in a moment. And I'd like you to play around with these sliders here. I'd like you to play around with the values of a, b, c, and d. And I would like you to tell me what's going to happen at various values of a, b, c, and d. Can you figure out some interesting cases? Let me show you what I mean. So here I've loaded up the Desmos graphing calculator. I'm going to type r of x is equal to, put a quotient bar in there, and let's put those terms in: x plus a, x plus b, x plus c, and x plus d. And let's just add a slider for each one of those. Now here you can see if they're all equal to 1, well, everything would cancel except for values at -1, where it would be undefined. Here we would have a hole. If all the values were 1, then the value would be undefined when x was -1, because that would make those terms 0. Now let's play around with things. Let's change the denominator's values a little bit. So here I have c at, let's say, 2. And notice how that makes an asymptote at -2. Let's change my d. Oh, I've summoned another one. Let's say d is 0. And now I have just an x here, because x plus 0 would just be x. You can see now I have these two asymptotes. Now also notice that I can alter around the a, and it seems to kind of bend and warp things, although it doesn't really bend the asymptote. But if I make that equal to one of the values below, it seems to cancel. What happened to my asymptote at -2? Well, it seems to be gone, but at the same time, there isn't a value at -2 either, because you still would divide by 0 if you plugged in a -2 here. And I really just want you guys to see a little bit more about how these graphs look, how they kind of play and break apart into pieces, how they form different numbers of curves. That's an interesting thing. How many components are there? When do they seem to merge or collapse or break from each other? See what you can tell yourself about this particular thought experiment. What are some interesting values here? Can you make things degenerate, right? Can you make things kind of collapse? And when does that seem to happen, right? This is an excellent tool for playing around with and trying to get yourself familiar with the rational functions. You can introduce other parameters here. You just play around with it. So this is your assignment, or if you choose to accept it, right, is to sort of experiment with some values here for these sliders and see all the wild and nifty behavior that can go on as you explore the rational functions. All right, that's actually it for today's video. Thank you very much for your patience and have a great day. Good luck with your studies. I'll see you in the next one.